Alright, in this video you're going to see some elements that we have discussed previously in either chapter 1 or 2, I can't quite remember, but we're going to be applying them to our discrete random variables. Okay, so what you see in this video should look pretty familiar to you. And in the video, for this video and the next video, we are going to be using pretty much one main type of example here. And it involves two different games. There's one game called Babo and another game called Zambo. And we're going to let the random variable, the amount of money we can win playing Babo, be X, and the amount of money we can win playing Zambo be our random variable Y. So it says in the game of Babo, a coin is flipped twice. If two tails come up, then you win $100. Otherwise, you lose $50. In the game of Zambo, a 10-sided die is rolled. If an even number comes up, you lose $25. If a 1, 5, or 9 come up, you lose $10. If a 3 or 7 come up, you win $50. The winnings or losings follow the probability distribution seen below. Okay, so we are going to fill in the probabilities here. Now, in a game of Babo, we're either going to lose 50 bucks or we're going to make 100 bucks. There is no cost to play either one of these games. All right, so it says if two tails come up, we win 100 bucks. So let's come up with real quick the different possibilities we can get from flipping a coin twice. And I'm just going to do a tree diagram here. We're either going to get a heads or tails on our first flip, and then our second flip, we're either going to get heads or tails. So altogether, we have 4 outcomes. We can have 2 heads, a heads and a tails and a head, and a tail and a tail. And this is the outcome that we want to see here. This is when we win $100. Okay, so 1 out of these 4, which is 25%, is when we win money. So here's 25%. Then it says otherwise we're going to lose 50 bucks. So the amount that we win will be negative 50 because we will owe 50 bucks. And if it's 25% for winning 100 bucks, then it's the complement of 25%. So we have a 3 in 4 chance because here are 3 out of 4 ways that we're going to lose 50 bucks. Okay? So here's our probability distribution for Babo. Now for Zambo, it says if an even number comes up, we're going to lose $25. So if we roll a 0, 2, 4, 6, or 8 on our 10-sided die here, so we're saying 0 through 9, we're going to lose 25 bucks. So that's half of our numbers here. So the probability that we're going to lose 25 bucks is going to be 50%. It says if a 1, 5, or 9 come up, which are all odd numbers, we're going to lose 10 bucks. So 1, 5, 9, there's 3 out of 10 options, so 30% that we're going to lose 10 bucks. If a 3 or 7 come up, then we're going to win. This is what we want to see. We're going to win our 50 bucks, so there's 2 numbers out of 10, so 20%. So there's our 2 probability distributions for the game of Babo that we're going to refer to as the random variable X, and Zambo that we will refer to our random variable Y. Now, what we're going to do first is calculate the mean, the expected value, and the standard deviation for each game in the long run. You can do this pretty easily in your calculator, especially the mean, the expected value. The standard deviation, it's going to take maybe a little while to do. Type it all into your calculator, but notice I didn't give you too much here to work with. Now remember the mean, we'll say for X here first, we're really going to multiply these values together, and then simply add it all together. So if you were to take this multiply plus this multiply, you should end up with negative $12.50. So this is saying if you were to play Babo in the long run, over and over and over again, that in the long run you're going to expect to make $12.50 in the hole. That you're going to owe, in the long run, $12.50 on the average. Okay? if we did the same thing for Zambo, if we were to multiply, add this, in the end you should get negative $5.50. In terms of the standard deviation, let me kind of run through again the calculator commands for doing that. So let's do with Bobo here. If you go to your list and let's do the amount 1, our X numbers here, represent list 1, and put the probabilities in for list 2, we know the mean's $12.50. The formula for the standard deviation was we wanted to add together all the individual X values minus the mean, square them, and then multiply them by their individual probabilities. Okay, so again, if you find the sum command, which was located if you hit second, and then list, go over to the math, and then down to number 5, sum. So this sum command will take care of that. X sub I, that's our first list value, minus the mean, which we already figured out here, was $12.50 negative. Now, if I subtract a negative $12.50, I'm really going to be adding $12.50. So make sure you keep an eye on that. If the mean is negative, you're really going to be adding the mean instead. And then we're going to say times the individual probabilities, which you saved as list 2. And then an end parenthesis for the sum command overall. Oh, I needed an extra set of parentheses in here. Let's see. I'll do that. So here's our sum parenthesis. Here's this parenthesis for this. So once you do that for Bobo, you should end up with $64.95. And if you do the same thing for Zambo, you should end up with $28.50. Okay, so make sure you have those values written down. Now, a little bit of a twist here. Imagine the proprietors of this game want you to feel like you have a better chance of winning more and losing less. So one day they offer a deal of adding $5 to all outcomes. The probabilities will stay the same. Fill out a new probability distribution table for each special game and determine the mean and standard deviation. Now, before we had a 25% chance of winning $100, but now in this special case they're saying you can add $5 more to that. So now we could win $105. And before we would lose $50 if we didn't get 2 tails. So they're saying add $5 to that. So instead of owing them $50, we only owe them $45 instead. And the same thing for our Zambo. We would owe $25 if we rolled an even number. Well, now we're only going to owe $20. If we rolled a 1, 5, or 9, we owe $10. Well, add 5 to that. Now we only owe them 5. And then rolling, what was it, a 3 or a 7, we would win, what was it, $50? Gee, go back here. Yeah, $50. So they're saying add 5 more to that. We're really going to win $55. So now, we're not just dealing with a random variable x anymore. We're dealing with our random variable x plus 5. We're taking whatever our previous amounts were that we could win or lose and adding $5 to them. So now, if you want to say this is list 1, this is list 2, then if we want to find the mean, and notice the way that I've written this, this is really mu subscript x plus 5. Okay, we're finding the mean of our new random variable x plus 5 added to it. Okay, so if we want to find the mean, we can take the sum command, and really we're just going to take list 1 times list 2. And that should give you what this is, which is negative $7.50. And if you want to figure out the standard deviation, then we're going to take the sum, and then a new parenthesis here, L1, those are individual x's, minus the mean, which was $7.50 negative, so that means we're really going to have to add $7.50, square that amount, and multiply it by the individual probabilities list 2, end parenthesis. And you should get $64.95. So now for Zambo. Now again, notice this isn't just mu of y plus 5. This is mu of y plus 5. Okay, where the y and the plus 5 are both in the subscript, like this. So now, if you want, you can either clear out list 1, list 2, or we could say now this is list 3 and this is list 4. If we want to find the expected value or the mean, we're going to take the sum of, we'll say, list 3 times list 4, and that should give you, basically you owe 50 cents, negative 50 cents. And if we were to take the sum, parenthesis, another parenthesis, L3 minus the mean, which in this case is 50 cents, so we're really going to be adding 50 cents, squared, then times list 4, the probabilities. If you were to type that in, you should get a standard deviation of $28.50. So now make sure you have those quantities written down. So now we're going to compare playing the regular version of Bobo and Zambo and the special version of Bobo and Zambo. The one thing I want you to notice immediately are the standard deviations. Notice the standard deviations of the special version of Bobo and the not special version of Bobo. They are exactly the same. Okay, so and we can say the same thing here for our special and non-special versions of Zambo, that the standard deviations are exactly the same. So whenever we add or subtract a certain value here to a random variable, in this case we added 5, did it really affect the standard deviation? It did not. Okay, so the standard deviation of any random variable plus or minus whatever that may be is still the same exact value as it was before. So basically we're saying that this plus 5 in the end really doesn't do anything. You can automatically, if you knew what this value was, it's going to be the same as this value right here. So you don't have to do anything. Adding does not change. And that was something that we had talked about before. That if you added a particular value to every value in a histogram, basically, that you're just shifting all your data, and the spread stays the same. It's that same concept. So the same thing here for our sigma sub y plus 5, that it's really just the same thing as sigma of your random variable y. But notice the means, they did change. But how much did they change by? You know, what is the difference here between negative $12.50 to negative $7.50? Well, there's a difference of adding 5, which is that little difference right there. So if you wanted to know what is the new mean if you knew the original mean, then all we have to do is, now notice here what I've done is I've kind of taken this plus 5 and I moved it up. It's no longer a subscript. So I'm really saying this is the original mean. If you knew what that was, which was that $12.50 here, that if you wanted to know the new mean of this random variable, all you'd really have to do is add 5 to it. And that's how we got the negative $7.50. Same thing with our Zambo game. If you notice, what's the difference between the old to the new? Well, all we had to do was add 5 to it. Okay? So the new mean of our y plus 5 version is really just the old mean of negative $5.50. Add the $5 to it. Okay? So the only thing that really gets affected here when you add or subtract is the mean and the median, which were our measures of center. Measures of spread, the standard deviation and the range, or IQR, were not affected. So when you add or subtract, only the mean, the mu, the expected value, is going to change. So I ask here at the bottom, did we really have to figure out a whole new probability distribution for both special games? And what I mean by that is, did we really have to do all of this? And the simple answer is no, we did not have to do this. Because all we really had to do in the end, let me clear all this out here, we knew that our old mean was negative $5 and, no, that's not right, it's for the other game, was negative $12.50. To figure out the new mean of the special game, all we had to do was add 5 to it, and voila, there it is. That's all we had to do. Same thing for our special version of Zambo. All we had to do was take the original mean of Zambo, which was negative $5.50, and then all we had to do was add 5 to it, and boom, somewhere there, there's our new mean for the special game. The standard deviations for both games, the same exact thing that they were in the regular version. They still have the same amount of spread. Okay, so again, adding and subtracting only affects the mean, does not affect standard deviation.
Now let's look at another example. Imagine the proprietors of these games want to increase the risk associated with playing Babbo and Zambo. All amounts will be tripled for Babbo and doubled for Zambo. Determine all possible winnings and their probabilities, the mean and standard deviation for each game. Okay, so it's not necessarily that it's riskier in terms of probability, it's just riskier because you can lose more money or you can gain more money, which has an extra appeal to some people. So if we're going to play triple money Babbo, then we can consider this 3 times our previous regular version Babbo game. So if before we could lose up to $50, now we can lose up to $150, but still with the same probability of 75%. And instead of winning $100, we could now win $300, still with, though, a 25% probability. And the same thing is going to be true for Zambo, except it's a double money Zambo. So instead of losing 25, we could lose up to $50 now. Instead of losing 10, we could lose up to 20. And instead of winning 50, we could win up to $100. Again, with all same 3 probabilities of 50, 30, and 20%. All right, so now if we were to look at the sum and the standard deviation of our triple and double games here, well, if we put in list 1 as our triple money Babbo and list 2 as still the probabilities of 75 and 25, if we do sum L1 times L2, if we do this command right here, we'll get a mean of negative $37.50. And if we do the standard deviation, which you can go ahead and type those in, if we do the sum, and again, we need 2 sets of parentheses to start out here. So we have list 1, which represents all of our x values here, or 3x values, technically. And then we need to subtract the mean, and here's our mean over here. So again, since the mean is negative and we're subtracting it, we're really going to be putting in a plus 3750 for the mean. And then make sure you end that quantity and square it, and then multiply by the probabilities, which are list 2 in this case. So, and then take the square root of all that. If you were to do that in your calculator, you will come up with an answer of $194.86. Now, this is a rounded number. This wasn't an exact value. And if I were to do the same thing with my double Zambo, again, maybe I call this list 3 and my probabilities list 4, then I would get a mean that comes out to be negative $11. And if I were to do the standard deviation, instead of typing in plus 3750, now I'd have to change it to plus 11. And I'd have to change my L1 to L3 and my L2 really to L4. Okay, because I need to use the same list for what I want to find the standard deviation of. And if I were to do that, I would get $57. So let's look at these numbers compared to our single games. All right. So before, when we looked at adding $5 to our games, the standard deviations were the same, whether you play the regular version or the +5 version. But the standard deviations now are definitely different. Okay. The one thing I noticed with this one over here is that my new standard deviation is twice the size as the old standard deviation. And where does that twice come into play? Well, we doubled all of our values. Okay, so this 2 right here does have a direct correlation to the standard deviation difference. Do I see the same thing over here with my 3 times game? And you do. It's not an exact, but it's pretty close, and it's because of the rounding effect. So our new standard deviation is 3 times the size of our original standard deviation. Okay, and we see the same thing happening with the means. The new mean is 3 times larger than the old mean, and our new mean for the double Zambo game is twice as large as what it was for the original game. So it looks to be that multiplication affects not only measures of center, as in our mean here, but it also affects our measures of spread, as in our standard deviation. All right, so the mean of our triple Bobo game, which was the negative 3750, was nothing more than just taking the original mean for just regular old Bobo and just multiplying it by 3. Okay? And the same thing held true for our double Zambo game. We just really had to take twice the regular version of it to get what its mean is. Standard deviations, this is where the multiplication effect does affect it. It is 3 times the old standard deviation and 2 times the old standard deviation. So when we multiply or divide b, and in this case b is 3 and 2, depending on which game you're looking at, to a random variable, it affects which measures? Well, we saw that it affected everything, which is, again, what we have seen previously back in Chapter 1, I think it was, when we talked about adding and subtracting a constant amount to all of our variables, or multiplying. And we saw that multiplying affected mean and standard deviation. So mean, or we could be talking about median, and standard deviation will be affected by that factor. In this case, the 3, and in this case over here, the 2. So did we really have to figure out a whole new probability distribution for playing these new versions of these games? No, once again, we did not really need to. So if I said, now I want to play a 5 times version of Bobo, what's its mean going to be? So what's the mean of the random variable 5x going to be? Well, all I got to do is take 5 times what the original mean was, and then I know what the mean of that 5 times game is. Same thing would apply with division. Like let's say the regular version, the X version, is just it's too much for people. They don't want to play. So I say, all right, well, I'm going to cut all my amounts in half. So instead of winning 75 bucks or losing, no, what was it? Instead of winning $100 and instead of losing $50, well, we'll cut it in half to say, well, you could win 50 bucks and you could lose 25 bucks. Those would be the half versions of our original X. Then all I'd have to do is take half of the old mean and half of the old standard deviation, and there would be my new ones. So that's all we have to do in those cases. So adding and subtracting, again, only affect measures of center, or mean and median, and multiplying affects both measures of center and spread. So our mean and our standard deviation are affected by both. And that is all for video number 4. So we'll see you for video 5.